now what I'm going to do is basically have a sort of gelling of various points that you've heard over and over again about community codes and software engineering practices, etc. The way I've organized this is the first part summarizes the motivation and the logistics, the community development, and best practices. So as far as the motivation and logistics goes, the question of why do you have community codes? Community codes do many, many good things. Some of those things are that scientists can focus on developing their own algorithmic needs instead of getting bogged down by things like infrastructure development. In communities that happen to have community codes, the graduate student arriving new is not going to start out by thinking about what to code, but instead they can plan on a more ambitious goal, getting further with their research. What they do is they look at the community codes available, find the ones that most closely match their needs, pick it up and customize it and get further. And they can also look at the amount of customization that they require. Here is the point that was just brought up in the previous talk as well, that it is important always to remember that they still need to understand the components that are developed by others that they're using, even if they don't actually have to develop them. There are some practitioners in the field who will state that no one should be using a code unless they have done their own development in those techniques, in those algorithms, because otherwise they don't understand what they're doing. And there may be some truth to it, but that goes too far. But it is absolutely true that unlike most other kind of software, people using scientific software have an extra requirement to really know and understand their tools and understand their valid regime and the places where you can use it, because it has been known to happen that a code was used in regime that it wasn't designed for and led to erroneous results. So it is important to know what you're doing with it. And as has been pointed out several times before, researchers can build upon work of others and get further faster. Code components that they develop can be reused. We've had a couple of examples in Flash where there were people who contributed code, not because they were particularly keen on sharing their code, but they realized that if they contributed to Flash, more people would become aware of their work and their citation will go up. So there is that incentive as well. The results will be more reliable because the codes have been better, not just better tested by the distributors, but also because the code will have, as there are more users exist, the code is exercised in more different ways, and therefore the code coverage in terms of looking at its functionality has had a better coverage, and the code is much more likely to have turned into a robust code. Because it is absolutely true that anytime you do develop a non-trivial piece of code, it takes many different ways of exercising it and many people doing different things over a long period of time that actually irons out the bugs and the deficiencies in the code. And of course, open source science results in more reproducible results. It's generally good for the credibility of the field. So there are two typical models in which the codes are developed, as pointed out by Eric Raymond. There is the cathedral model and there is the bazaar model. The cathedral model is that even if the developers are spread over, there is a central gatekeeping entity that keeps control over what goes into the code and monitors the quality of the code, whereas the bazaar model is that code is developed in view of public, and the bazaar model is what Raymond credits Torvalds, the leader of Linux, as the inventor of the process. And this has a distributed control model. The scientific codes, by and large, follow the cathedral model. There are a few exceptions to it, and they have their own challenges, like ENSO is an exception to it. And ENSO has had some challenges with regards to its quality control and with regards to convergence on prioritizing what goes next into the code, etc. So there is that. There are many reasons that are given for it. Some are valid, and some just spring from the bias of the scientists that have traditionally been more inclined to keep their code close to their heart for various reasons. The valid reasons happen to be that as I said, the code quality can become hard to maintain if anybody and everybody can contribute, because people may want to contribute things without necessarily understanding all the various aspects of the code. It is hard to find support for gatekeeping and general maintenance in a code like that. And also, in many of these communities, the communities are far too small to keep a vibrant contribution. I mean, the critical mass of contribution going on if it is to effectively support the bazaar model. And the reward structure is completely incompatible. But there are other reasons given that at least in my opinion, are not so valid. One of them is these codes are too complex. So what? As long as there is a quality control, it doesn't matter that they're very complex. And well, this one, that not sharing the code gives you some sort of a competitive advantage is also not just for the reasons that Sean gave you earlier about not knowing about any situation where you got someone took a march ahead of you in getting result, and because you see, code is basically a tool. Your research, if it is dependent upon you being able to use a tool ahead of everyone else, means that it is really not that innovative of a research. Your ideas are what make a contribution to your research. So you should, if you are insecure about your ideas, then you really are not at the cutting edge of the research. And that's really a specious argument about having a competitive advantage because of it. So the real reason many times is simply just the history of development and the pride of ownership, and nothing else. And sometimes people just want to keep the code to themselves, because in terms of yeah, never mind. It's just the pride of ownership and nothing else, really. The benefits of the bazaar model, many of them were pointed out, is that given large enough population, there are more eyes on the code, therefore bugs are found faster, more varied test cases, debugging is parallelized, and the infrastructure limitations are quickly exposed. More people contributing to the code means more the capability addition is rapid, codes can do more. What that also means is it causes a good extensible design to happen, and also because users almost always want to customize or extend the code in some way, so that gets incorporated into the design. Greater knowledge pool operating together, therefore there is a greater possibility of innovation. The pitfalls of the bazaar model, many of the benefiting reasons can go the other way around, because bigger knowledge pool can also mean that there are many more conflicting opinions and therefore more divergent ideas for where you should take the code. And this is a problem that has been faced by codes that do bazaar model of development. So prioritization can become extremely challenging, and gatekeeping can become a challenge, because the scientific codes as it is have their own peculiarities of verification and validation. And so the orchestration of capability combination becomes difficult when when you have this kind of a capability explosion, because many things just will not play very well together. And then I thought I'd spend some time elaborating upon the various ways in which, because this was a question that was raised earlier today about the path that codes can take in becoming a community code. So a common path that happens very often is that someone wrote a very useful piece of code, the group started using it, the alumni of the group went to other places, and in their new places, they started developing their own groups that use the code, and soon the code has become popular. In these situations, there was no focus, and there is very little software process involved. What ends up happening in this case is either the code will undergo a major refactoring process to incorporate some process if it continues to build, or else it will have a limited shelf life, and another group of people will come around, they'll decide, or it may happen that the code has gone beyond a critical mass at which you can still refactor and keep it effective, and so people will abandon that code and start writing from scratch again, and the whole cycle goes, which is actually not a particularly useful cycle. So a more sustainable path is that enough like-minded people decide that, that something more needs to happen. So what they decide is that there is this much of code available that if they were to reuse the components from this code and could leverage it, that they can go much further. So they spend time and invest some time to design, effort and time to design in the code and architected for extensibility. So, and they plan for future growth, and they basically, along with the growth of the code itself, the community supported model also grows. This model is still relatively rare, but the instances are growing. More because as models have gotten more complex, people have realized that they do need to be able to leverage work of the others, otherwise they will not get where they want to get with their science. A desirable path, which should have been growing, but is actually retreating much more, is this, that there is explicit funding to build code for a target community, which has an implied support for the design phase, and outcome is expected to be long-lasting and well-engineered. This is the model under which several of the codes that have had the longest lifespan were developed. Cactus was one of them, Samurai was one of them, Flash was one of them. I think several of the molecular dynamics, including NW Chem, was one of them. So there was a time in the late 90s with that a huge amount of investment was made in code, software architecture research, and many of the frameworks were developed. And among those, the ones that kept a close communication going with their target science communities actually survived and have been the basis for these long-term, long-living community codes. But this model, for some reason, has not gained traction since that time, and that kind of funding has not been possible to get. So this is getting increasingly harder. But when it does work, you do get longer lasting and more capable codes. The next thing is I wanted to recap things that have been talked about community development so far. So what are the communities that tend to have community codes more often than others? You will notice that this is true, that some communities have a lot of community codes, other communities seem to have smaller efforts and their own smaller codes that they work. It is usually true that community codes grow much more in those areas of science where, in order to make any headway in scientific discovery, you need multi-component, multi-physics models. For the simple reason that in those communities, in those kinds of research areas, it just isn't possible for one person to sit down and put in everything in their code and make any head. It's the upfront cost of building your tool is just simply too high. And so these communities are much more amenable to leveraging each other's works and making an advance together. The other model in which the community codes develop is, for example, a visionary will see the benefit of software reuse and release the code that they develop for their own purposes. In fact, this is pretty much what happened in the astrophysics community in the early days. It was among the very first communities that started to have a model of community code because Zeus was released to public like in the 80s, way before anyone else had even thought about releasing the code. And so a culture grew around it, and people quickly saw the advantage of it. The outcome of having these kind of community codes is that the sophistication in modeling advances much more rapidly in these communities. But the communities that do not follow this model, the ones that are much more prone to keeping their software closed, they just have repeated reinvention of wheel, and the general advancement of model fidelity is slower. Though there are some communities where the building of the tool is relatively easy, relatively simple, and one simple tool can go a long way in letting them have their, it doesn't take very long to build a tool and do their science with that tool over and over again. And this is a sort of an anecdotal evidence of it, but what I have seen in looking at the papers that were published out of Flash, for example. Flash is used by some 6 or 7 different communities. The communities that, the research areas that have required use of 50% or more of Flash capabilities in a single simulation have had more publications using the Flash code than the communities which use maybe 1 or 2 solvers of Flash. because they have many more of their own codes that they use and publish. So, for example, all of the supernovae papers, there are many more supernovae and star formation publications that have come out of Flash than there have been in solar physics, because many times in solar physics, you're just interested in the turbulence and the convection. And it's much easier to develop code for it. So what does it take to build a community code? A community is not built by just popularizing the code, or even customizability by itself does not make a code community. So what does it take? In order to build a community, you need to have people who are using the code also be able to contribute to the code, to be able to grow the code, and to have recognition for their contributions. So you want to be able to enable contributors from users and provide support for them. It is very important to make policy for balancing the IP protection and open source needs. You should have relaxed distribution policies, which means that collective ownership to group of users so that they can modify and share among themselves as long as they have the license is a good way to encourage a community. In general, more inclusivity implies greater success in community building. And this has been repeatedly seen by many, many different projects, is that the less open a community is to accepting input from their community of users, the less successful they are in growing and in sustaining the projects. Another thing that is given in an investment in robust and extensible infrastructure and a strong culture of user support are both prerequisite. So in contribution policies, one has to think about balancing contributors and distribution needs, maintainable code requirements, that is minimum set needed from the contributor. For example, people talked about pull requests. When would you accept a pull request and when would you reject a pull request? You would accept a pull request when a person has done the due diligence, in the sense that they have tested their code, they provide a test that you can incorporate in your automated daily test suite, and they have documentation, and they make some commitment to provide support to the users. If you get that commit from a user and you run your own tests, you're much more likely to accept that contribution coming from a user than otherwise. Another possibility, of course, this is a model that we've played with at times off and on, is the add-ons, which means that you don't necessarily include every bit of code in the distribution and take responsibility for it, but that you make a provision for add-ons, which means that you can say that these are the additional capabilities that you can utilize, but that these are not supported by the core distributing team, but that the people who are distributing them will be supporting these, but we make sure that they interoperate with one another. And then we thought it would be a good idea to see what many of the communities use in terms of common best practices, etc. So there is a project that was mentioned several times. This is the IDEAS Software Productivity Project, which is a collaboration between the BER Office of Science and ASCR. And so there are several codes that the idea was for the expertise of the software engineers brought over to these domain scientists so that they could improve their codes and their productivity. So we took a survey of the practices being in use by these codes. So what we found out was that all of them do use version control, and all but one of them use distributed version control. Builds are evenly divided between GNU Make and CMake. They all provide some sort of documentation and some form of user guide. Many also use automated generation tools. They also all have testing in some form. Some of them do manual regression testing on a sporadic basis, but many also have automated. Roughly half of them make use of unit testing capability, and majority are publicly available. Now, this actually came as a bit of a surprise, because even until 2 or 3 years ago, if you had run the same kind of a survey, the results would have been very different, because there were many more closed codes and people weren't so much given to software engineering practices. So this was a pleasant surprise, because to contrast that with the codes that we tried to invite to a workshop in 2012 on community codes, there were very few codes that would qualify as the codes who were doing software practices that were generally useful. So here, the general features that we found were the software architecture was in form of composable components that was always needed for extensibility. They all had a rigorous auditing process in place. There was gatekeeping for contributions, even the individual models for gatekeeping were different. All codes had wide user communities, and communities all benefited from a highly exercised code base. There are many communities that are headed towards building community code, some of them because of it being imposed upon them by their funding agency, and some others because they've realized that that is a much more productive way of doing science. So for example, ACME is one community that is going from being a very, very, very fragmented community with each group having its own standards that did not work with each other into a well-integrated, complete climate model, and this was mandated by the DOE. And I recently started working with this project, and over the years I had heard what I can only describe as horror stories of what was happening in the climate modeling community. And this project is like less than 2 years old right now, and it was such a pleasant surprise to me to find so many practices in place and people open to talking about incorporation of software engineering practices, that I think that this project actually has a very good chance of success, contrary to what people were predicting in the past. And then I've had conversation with people in the accelerators community, which is still very, very fragmented, and there are many codes that are the huge amount of redundancy in the codes, many, many replicated codes. At least the community has realized that that is not a sustainable model, so they've started having workshops, and the outcome of those workshops comes out in the form of white papers which state the advantages of combining efforts and having common community tool set that the whole community can use. So they've written white papers about it. And their objective is to avoid duplication and get some convergence. So this is one community. Another community that I haven't listed here but is local here at Argonne is the people who are doing the environmental work. So these people basically put sensors in places, and what they want to do, they want to have software that allows them to figure out which would be the best place for putting sensors. And even this community, which is relatively new to computation, is thinking in terms of software practices and having a community building. So this is all very, very positive and good thing. So the common threads are that all of them have open source with governance structure in place. Trust building happens among teams. There's commitment to transparent communication, strong commitment to user support. And this is another thing which is common among most of these codes, is either an interdisciplinary team or a group of people who are comfortable both with domain science and software development and engineering. There is always attention to software engineering and documentation, and there is an understanding of benefits of sharing as opposed to being secretive about the code. To summarize the best practices over again, all of them, the basic software process they all have is they have invested in extensible code design, they use version control and automated testing, rigorous verification and validation, coding and testing standards, clear and well-defined policies for auditing and maintenance, distribution and contribution, documentation. The others which are desirable but are not as pervasive are provenance and reproducibility, lifecycle management, for the simple reason that the general software engineering lifecycle models do not apply to scientific software, and we haven't yet converged as a community on a good lifecycle model that works well for the scientific code development. Open development and frequent releases is something that is desirable but doesn't necessarily happen everywhere. As I said, many of these practices have been covered in earlier lectures. A useful resource when they are getting into the business of developing code is this collection of how-to and what-is documents that are being compiled by the Ideas project. Mike talked about them yesterday. These are what he calls the bite-size information about getting going with software engineering practices. And this is something on which we would very much welcome contributions from the community to make these documents more useful. For example, you can visit them, see the documents there are. If you think that there is some document that would be helpful, you can write to us in the project, and we would see to it that those documents are produced. And we can even take input from you in terms of what you want to see in there. And these are various other resources that you can, the slide is there, so you can just find those resources. And the last thing that I was going to do is interdisciplinary interactions, and this is part of the extension from the sociology, is that interdisciplinary interactions are challenging, and it's important to make them work well for a code project to be successful, as we found ourselves through hard experience. Science users should treat code as a research instrument that needs its own research, and it needs its own innovation. A model in which the developers are treated as second-class citizens is not very conducive to a good interdisciplinary interaction and productive code output. It definitely helps to have people with some multidisciplinary training, and there should be comparable resources and autonomy for developments and recognition of their intellectual contribution. And there should all be a very careful balance between long-term and short-term objectives. And I think with that, I come to an end, and I leave this as the last thought to you, that it is extremely important to recognize that science through computing is only as good as the software that produces it. I mean, it is possible that for you to do worse than what your software allows, but you cannot do any better than what your software allows.